A little more than 800 million light-years away, two dark bodies are falling together. One is a black hole, more than 20 times the mass of the Sun. The other carries about 2.5 suns inside a space so small that no telescope can resolve it. It may still have a surface. It may already have a horizon. For a few final seconds, the difference is hidden inside the shape of a wave moving through space. Before that wave reaches the detectors, take a moment to settle into wherever this recording has found you. If these quiet science stories help make the evening feel slower, you can leave a like, subscribe, or share the video with someone who also enjoys listening to the universe. After the day has gone still, and perhaps leave a comment with the place you are listening from and the hour showing on the nearest clock. The same signal can arrive in rooms separated by oceans, under different skies, while the event that created it has already been over for hundreds of millions of years. Lower the lights if they are still bright. Let a fan or some steady background sound fill the room. Find a position that does not need to be adjusted again. There is nothing here that needs to be memorized. The measurements can pass by slowly, one after another, while the body becomes heavier and the room recedes a little. Inside the long vacuum arms of LIGO and Virgo, laser light travels towards suspended mirrors and returns to meet itself. For almost all of the night, the pattern remains unchanged. Then space stretches in one direction and narrows in another. The mirrors barely move, yet the returning light is no longer quite the same. Hidden inside that difference is an orbit, two masses, and an object that has reached the edge of every familiar name. The signal is given a name only after it has already passed. GW190814 is a label built from a date, but the name does not describe what the instruments have found. A rising pattern appears in the data from the two LIGO observatories and Virgo in Italy, each detector recording the same change in space-time at a slightly different moment. The signal lasts only a short time in the sensitive band, yet its shape carries the motion of two compact bodies approaching the end of a long orbit. By the time the frequency enters the range of the instruments, most of their shared history has already disappeared into the past. One object is heavy enough that its identity causes little debate. Its mass is a little above 23 times that of the Sun, compressed inside an event horizon. No known neutron star can support anything close to that weight. The smaller companion is different. Its mass falls between roughly 2.5 and 2 2/3 times the mass of the Sun, depending on the exact combination of parameters allowed by the signal. That interval is narrow enough to make the problem clear, and wide enough to leave the answer open. The object is heavier than any securely identified neutron star known at the time of the discovery, but lighter than the black holes commonly measured in X-ray binary systems. The two bodies are badly mismatched. The larger one carries close to 9 times the mass of the smaller. Equal companions pull on each other in a more balanced way. Here, the lighter body travels through a gravitational field dominated by the heavier one. It is not passive, and its mass still alters the waveform. But the asymmetry is written into the signal. The smaller object behaves almost like a compact probe, descending through increasingly curved space-time. Nothing about the detection provides a direct image. There is no bright point to enlarge, no surface to examine, and no surrounding gas outlining the orbit. The event is reconstructed from changes in distance smaller than an atomic nucleus compared with the length of the detector arms. Those changes repeat across the network in a form consistent with a gravitational wave, moving through Earth, The pattern rises in frequency as the orbit tightens. Its strength grows. Then the separate motion ends, and the system becomes a single remnant black hole, settling into a quieter state. The measured masses come from that structure, rather than from an assumption about what the objects should be. General relativity describes how compact masses radiate energy through gravitational waves as they orbit. Energy leaves the system, the separation decreases, and the motion accelerates. Different combinations of mass produce different rates of change. A light pair remains in the detector band longer. A heavy pair moves through the final frequencies more quickly. A strongly unequal pair carries another pattern because the balance between the two bodies alters the phase evolution. The waveform is compared with large families of predicted signals representing possible masses, spins, orientations, and distances. The combinations, consistent with the data, form the range reported by the observatories. This method does not require the smaller companion to be called a neutron star or a black hole before it is weighed. The orbit is measured first. Classification comes later. That order matters because familiar names can pull interpretation toward familiar populations. A body near 1.5 solar masses would naturally be placed among neutron stars. A body near 10 solar masses would fit comfortably among stellar black holes at roughly 2.6 solar masses. The measurement reaches a region where the name cannot be assigned by weight alone. The older picture contained what is often called the lower mass gap. Neutron stars found through radio pulsars, generally gathered below the region, occupied by black holes found through X-ray binaries. The gap was never a forbidden zone written into general relativity. It was an observational pattern, supported by ideas about how massive stars collapse. When a dying stellar core remains stable, it can leave a neutron star. When collapse continues and surrounding material falls inward, the remnant may pass beyond the neutron star limit and gain enough additional matter to become a black hole of several solar masses. That process can produce a jump rather than a smooth sequence. A quiet interval in a catalog can have more than one meaning. It may reflect a real shortage created by stellar evolution. It may also reflect the ways astronomers find dark objects. Pulsars reveal themselves only when their beams cross Earth. Black holes in X-ray binaries become visible because gas from a companion heats before falling inward. Compact objects without a useful beam, a feeding companion, or a luminous environment can remain absent from both groups. Gravitational waves open another route. They do not require a surface to shine or gas to glow. They require only that two compact bodies come close enough to merge. GW190814, therefore, does more than place a single dot inside an uncertain interval. It shows that the interval can be reached by observation. At least one compact object with a mass near the old gap has taken part in a merger. One detection cannot establish the shape of an entire population. Still, the emptiness is no longer complete. The blank space now contains weight. The lack of light after the event appears to offer a simple clue, but it does not provide a simple conclusion. Follow-up observatories. Search the region of sky identified by the detector network. No confirmed optical, X-ray, radio, or gamma-ray counterpart is linked securely to the merger. A pair of black holes would naturally remain dark in an environment without much gas. A neutron star could produce light if tidal forces tear it apart before it crosses the larger black hole's horizon, leaving hot matter outside. Yet disruption is not guaranteed. A black hole above 20 solar masses can swallow a compact neutron star with little material escaping, especially if the star is small and the black hole's spin does not favor early disruption. In that case, a body with a surface can disappear almost as quietly as a body that never had one. The distinction remains real in physics, but hidden in the observation. Before the plunge, one object would contain a crust, a dense interior, and matter pressed beyond nuclear density. The other would contain no accessible surface. From far away, both can leave a waveform with little or no light. The larger black hole can remove the easiest evidence by carrying the smaller companion across its horizon before the companion's material, nature, becomes visible. The event is uncomfortable. In a useful way, the data are not weak. The signal is clear enough to place the smaller object where established categories overlap. Greater uncertainty would make the case easier to ignore. If the mass range extended comfortably into the ordinary neutron-star population, or the familiar black hole population, the problem would soften. Instead, the measurement remains centered, where both interpretations demand an unusual story. If the companion is a neutron star, then matter supports more mass than many models allow. The object must remain stable while carrying close to 2.5 suns inside a body no wider than a city. Its core may contain states of matter that cannot be reproduced in bulk on Earth. Yet those states must continue producing enough pressure to resist collapse. It would be one of the heaviest neutron stars nature has made, surviving near the final limit where a surface can still remain outside a horizon. If the companion is a black hole, then stellar evolution, or some later process, has produced a horizon at a mass lower than the older black hole population suggested. The object may come from an unusual collapse, a stripped star, a neutron star that gained mass and failed, or an earlier merger whose remnant later found another partner. The final collision would then be easy to understand as a dark black hole merger, while the earlier history would become the harder problem. The waveform itself does not choose between those histories. It gives masses, a distance, a strongly unequal orbit, and a final black hole. It places limits on spin and the geometry of the system. It offers little evidence of tidal deformation from the smaller body. But that absence is not decisive. A compact neutron star can leave only a weak tidal trace. When paired with a much heavier black hole, the signal weighs the companion more clearly than it reveals whether the companion can bend, crack, or hold a surface. GW190814 enters astronomy as a measured ambiguity. It is not mysterious because nothing is known. Much is known. The masses are constrained. The asymmetry is clear. The merger is real. The larger body is a black hole. The missing piece is narrower and more difficult. Whether the smaller object resists gravity with matter or has already surrendered that distinction to an event horizon. The wave has crossed Earth and moved on. The mirrors return to their usual positions, and the laser pattern settles. The source itself has long since become a single black hole, carrying both possible histories inside the same final horizon. What remains outside is a recorded strain, a sequence of numbers, and a companion whose mass has been measured more securely than its name. The next step begins inside the instrument, where geometry is turned into evidence, one fraction of a wavelength at a time. The instrument begins with a simple comparison. A beam of laser light is divided into two paths that run at right angles through long vacuum tubes. At the far end of each arm, a mirror hangs in isolation, protected as carefully as possible. From the ordinary movement of the ground, the light reflects, returns, and meets the light from the other arm. When the distances remain unchanged, the returning waves maintain a stable relationship. Their peaks and troughs combine in a familiar pattern. Nothing dramatic appears. The detector waits inside that balance. A gravitational wave changes the balance by changing the space through which the light travels. One arm becomes slightly longer, while the other becomes slightly shorter. Then the pattern reverses. The mirrors do not need to be struck by anything. No particle arrives and pushes them aside. Space-time itself changes shape, and the laser records the difference because its two paths no longer return in exactly the same phase. The effect is smaller than ordinary language handles well. Across arms several kilometers long, the change is less than the width of a proton. The measurement succeeds not because the disturbance is large, but because the comparison is repeated with extraordinary control. The passing wave does not carry an image of the source. It carries rhythm. Early in the final orbit, the two compact bodies circle at a lower frequency, losing a small amount of orbital energy with each cycle. As the separation falls, the motion becomes faster. The waves arrive closer together. Their amplitude grows because the acceleration becomes stronger, and the system radiates more power. In the detector data, this produces the rising sweep, often called a chirp. The name sounds almost light, though the source is the last motion of two objects whose gravity has bent the surrounding geometry far beyond ordinary conditions. The chirp is not identical for every binary. Its pace depends strongly on a combination of the two masses, known as the chirp mass. This quantity governs how quickly the frequency rises during much of the in-spiral. A system with heavier components passes through the observable frequencies differently from a lighter one. The total mass also influences where the final orbit ends, and how much of the merger appears inside the detector band. Mass ratio changes the shape again. Two similar objects share the motion more evenly. A system like GW190814, with one body close to 9 times heavier than the other, leaves a distinctly unequal imprint. Spin adds another layer. A compact object rotating in the same direction as the orbit can allow the system to remain in a tight configuration for longer than an object spinning against it. Misaligned spin can cause the orbital plane to wobble, producing precession and subtle changes in the waveform. In GW190814, the data constrain some combinations of spin more clearly than others. The larger black hole dominates the angular momentum budget, while the smaller companion remains harder to read. A rapidly spinning neutron star, or a slowly spinning black hole, can hide inside overlapping regions of parameter space. The waveform narrows the possibilities without forcing a single identity. Distance is carried through amplitude, but amplitude cannot be read alone. A nearby source generally produces a stronger strain than an identical source farther away. Orientation changes the observed strength as well. A binary seen nearly face-on sends a different pattern toward Earth than the same system viewed near the edge of its orbital plane. Distance and inclination can imitate parts of each other. The reconstruction therefore treats them as linked quantities, allowing many possible combinations and testing which group best fits the full signal. This is why a gravitational wave measurement is not a single number pulled from one peak. The observatories compare the recorded data with large banks of theoretical waveforms built from general relativity. Each waveform represents a possible binary with particular masses, spins, orientation, distance, and sky position. The analysis asks how well each papillapiti matches the signal after accounting for noise. Better matches receive greater statistical weight. The final result is a landscape of probability, rather than one perfect point. Noise is present at every stage. The ground shifts under ocean waves, weather, traffic, and distant human activity. Suspended mirrors carry thermal motion. Laser light has quantum fluctuations. Electronic systems add their own small disturbances. Many local events can create brief patterns that resemble a signal in one detector. A true gravitational wave must appear consistently across separated observatories, with the right differences in arrival time and phase. GW190814 was recorded by both LIGO detectors and Virgo, allowing the network to test whether the disturbance behaved like one wave crossing the planet rather than one instrument experiencing a local fault. The separation between the sites turns time into direction. A wave reaches one detector first, another a few milliseconds later, and the third after a different delay. Those differences limit the region of sky from which the wave could have arrived. Detector orientation matters because each instrument responds differently depending on the direction and polarization of the wave. Combining the three responses reduces a broad ring of possible locations into a smaller patch. The result is still not a sharp image or a single galaxy. It is a probability map spread across the sky. That map guides telescopes searching for light. In GW190814, follow-up teams examined many possible host galaxies and transient sources inside the localization region. No confirmed electromagnetic counterpart emerged. The gravitational wave network had located the event well enough to make those searches meaningful, but not well enough to identify one host without additional evidence. Geometry supplied a region, not an address. The waveform also gives access to the final moments of the orbit, where gravity becomes too strong for Newtonian descriptions to remain sufficient. Far apart, the bodies can be pictured as masses circling a common center, while slowly losing energy. Near merger, space-time curvature shapes every part of the motion. The inspiral accelerates into a plunge. The two-body description gives way to a single distorted black hole. That remnant vibrates briefly, releasing gravitational waves at characteristic frequencies before settling into a stable state. This fading stage is called ring-down. For many black hole mergers, inspiral, merger, and ring-down can all contribute to the measurement. GW190814 is especially informative during the inspiral because the strong asymmetry leaves many orbital cycles in which the lighter body traces the gravitational field of the larger one. Those cycles help determine the mass ratio with unusual precision. The final black hole is still important, but the central classification problem belongs to the smaller body before it disappears. If the companion had a material surface, tidal forces could have altered the signal. The gravity of the larger black hole would pull more strongly on the near side of the smaller object than on the far side. A neutron star would deform slightly, and that deformation would feed back into the orbit. The resulting phase shift is small, accumulating over time. Its size depends on how compact the star is and how its interior responds to pressure. A black hole, under the standard description of general relativity, does not carry the same material tidal response. In GW190814, no clear tidal signature was measured. That fact does not settle the classification. A very compact neutron star deforms less than a larger one. The large mass ratio also reduces the opportunity to isolate the effect before the smaller body enters the larger horizon. Instrument sensitivity places another limit. A signal may contain a physical feature too faint to distinguish from the surrounding uncertainty. The absence of a measured deformation therefore means that no strong tidal imprint was required by the data. It does not mean that a surface was proved absent. The distinction reveals both the power and the restraint of the method. Gravitational waves can weigh objects that emit no light, trace their orbit, estimate their distance, and follow their final motion through strongly curved space-time. Yet mass and motion do not always reveal composition. Two bodies with the same mass can shape much of the inspiral in nearly the same way if one is a compact neutron star and the other a small black hole. The difference lies in effects that are weaker, later, or hidden behind the larger black hole's horizon. The measured mass of the smaller companion survives all these uncertainties. Changes in spin, distance, and orientation shift the allowed range, but they do not move it into an ordinary part of either familiar population. The probability remains concentrated near the old boundary. The instrument has therefore done something precise, without doing something complete. It has shown where the object belongs in mass, while leaving open what kind of object can occupy that place. After the analysis is finished, the original disturbance remains almost austere. A pattern of laser interference changes for a short time. 3 observatories record related traces. General relativity connects those traces to an orbit, and statistical inference turns the orbit into masses and spins. No surface enters the detector. No horizon appears on a screen. Geometry becomes evidence, but evidence has layers. The first layer gives the weight of the companion. The deeper layer, the one that would reveal whether matter still held itself outside a horizon, remains faint. The larger body, in GW190814, is the easier one to name. With a mass a little above 23 times that of the Sun, it lies far beyond any credible neutron star limit. No known arrangement of dense matter can support such weight as a stable object with a surface. Its identity is fixed by mass alone. It is a black hole, and during the final orbit, it creates the deeper gravitational well, through which the smaller companion must travel. That certainty does not simplify the whole event. It gives the mystery a frame. The heavier black hole is ordinary enough to recognize, yet massive enough to hide the very evidence needed to identify its partner. The smaller object approaches from outside, carrying either a material surface or an event horizon of its own. From a distance, those possibilities remain distinct. Near the larger horizon, the difference can become almost impossible to observe. A neutron star has a surface. It may be only a few tens of kilometers across, but matter ends there and open space begins. Light emitted above that surface can still escape, though its path is bent, and its energy reduced by gravity. A black hole has no visible surface. Its event horizon is not made of material. It is a boundary in space-time, a place beyond which every future path points inward. The distinction is sharp in physics. One object contains matter, compressed nearly to collapse. The other has already crossed the condition where collapse can no longer be reversed. The final approach tests whether that distinction leaves any trace outside the larger black hole. As the smaller body moves inward, gravity is not equally strong across its width. The near side is pulled more strongly than the far side. This difference is called a tidal force. On Earth, tides raise oceans by a small amount. Near a stellar black hole, the same basic effect can stretch a compact star, distort its shape, and eventually tear matter away. Whether disruption happens depends on a race between two distances. One is the distance from the black hole, at which tidal forces become strong enough to break the neutron star apart. The other is the distance at which the star crosses the black hole's horizon, or enters an orbit from which no stable path outward remains. If the tidal disruption radius lies outside the critical black hole region, pieces of the star can escape immediate capture. If it lies inside, the star disappears before a large amount of matter can remain visible. The mass of the black hole shifts this balance. A very small black hole can produce severe tides outside its horizon, because its horizon is compact compared with the size of the neutron star. A more massive black hole has a larger horizon. The neutron star may cross that boundary while still mostly intact. GW190814 contains the second kind of system. The black hole is heavy enough that prompt swallowing becomes plausible, even if the companion carries a surface. The neutron star's own structure matters just as much. A larger star with a less compact interior is easier to deform. Its outer layers feel a greater difference in gravity across the star, and disruption can begin farther from the black hole. A smaller star with the same mass is more tightly bound. Its material stays together longer, bringing the surface closer to the horizon before it begins to fail. A neutron star near 2.5 solar masses, if such a star can remain stable, would probably be among the most compact neutron stars in nature. This creates an unexpected agreement between the two main clues. The same dense interior needed to support an unusually heavy neutron star could also make that star difficult to tear apart. A surface may exist, yet remain hidden because it survives until the final plunge. The lack of light would then follow, not from the absence of matter, but from matter being bound too tightly to escape. Spin changes the geometry again. A rotating black hole drags nearby space-time around with it. If the spin points in the same direction as the orbit, the innermost stable path can move closer to the horizon. Under some conditions, this allows the neutron star to orbit deeper before falling, which can either increase or reduce the chance of visible disruption, depending on the balance between the orbital geometry and tidal forces. High-aligned spin often gives matter more opportunity to remain outside after disruption. Low spin, opposite spin, or a poorly aligned orbit tends to make a dark plunge more likely. The signal from GW190814 constrains the black hole's spin, but it does not reveal every detail with enough precision to reconstruct the final encounter uniquely. Several combinations remain compatible with the data. A neutron star can therefore fit inside some allowed histories, without producing a bright counterpart. A small black hole fits as well. The larger horizon accepts both possibilities. The moment of disruption, if it occurs outside, changes the gravitational waveform. A neutron star that begins to lose its shape no longer behaves exactly like a point mass. Its internal structure absorbs and redistributes part of the orbital motion. The wave phase shifts by a small amount. If the star is torn apart before the final plunge, the signal can end differently from a clean black hole merger. Matter left outside may settle into a hot disk, flow along magnetic fields, and release energy through several channels. No clear disruption signature appears in GW190814. The waveform remains consistent with a compact object, entering the larger black hole, without leaving a strong material imprint. That outcome is expected for two black holes. It is also possible for a neutron star that is small, heavy, and swallowed early. The measurement reaches the boundary but does not expose what crossed it. The search for light faces the same difficulty. Material outside the horizon would have to be heated or ejected in sufficient quantity to become visible across the event's distance. Some of it might form a brief glow, powered by radioactive decay. A disk might feed a short burst of high-energy radiation. Outflow moving into surrounding gas might produce a later radio or X-ray afterglow. Each possibility depends on how much matter survives, where it moves, and whether the radiation is directed toward Earth. If the neutron star crosses nearly whole, those signals fade before they begin. The crust, core, magnetic field, and any matter carrying the record of the star's composition pass inward together. No fragment remains outside long enough to cool, expand, or shine. The event then appears dark for the same practical reason as a merger between two black holes. The difference exists before the horizon is crossed, but almost none of it is allowed into the observable aftermath. The larger black hole, therefore, plays a quiet but decisive role. It is not the strange object in the system, yet it sets the conditions under which the strange object becomes unreadable. Its mass determines the size of the horizon. Its spin shapes the last stable paths. Its gravitational field controls the tide. By the time the smaller companion reaches the place where its surface would matter most, the geometry may already have removed that surface from view. This also explains why the event cannot be understood from mass alone. A neutron star beside a lower mass black hole might have been torn apart earlier, leaving light and a clearer tidal imprint. The same neutron star beside a heavier black hole can vanish without display. Identity and circumstance become entangled. The object may possess matter, but the system decides whether that matter becomes observable. The asymmetry of the pair strengthens this effect. In a merger between similar neutron stars, both bodies carry surfaces, and both contribute strongly to tidal deformation. Matter can collide, heat, and escape in several directions. In GW190814, the lighter companion enters a field dominated by a single large horizon. There is no second material surface waiting on the other side. The encounter is less like two stars colliding and more like one compact body being tested against a region from which no signal can return. For a short time, the smaller object still remains outside. Its orbit accelerates, the curvature grows. If it is a neutron star, pressure and nuclear forces continue to hold its interior together, even as the tide pulls across it. If it is a black hole, nothing material resists. The waveform records nearly the same broad motion in both cases. Then the last stable path ends. The surface, if there is one, passes through the horizon. From outside, no later observation can recover it. The final black hole settles, carrying the smaller object's mass and angular momentum, but not a readable label describing what that mass once contained. A star and a hole can arrive at the same remnant by different routes. GW190814 leaves those routes folded together. The larger body is known. The smaller one is weighed. The final remnant is a black hole. What remains uncertain is the brief interval before the plunge, when a surface may have existed only a few kilometers beyond a horizon that was already waiting to erase its evidence. A neutron star is born, after an ordinary form of support has already failed. During the life of a massive star, heat and pressure from nuclear fusion push outward while gravity pulls inward. That balance can last for millions of years. Near the end, the core fills with iron, an element that no longer releases useful energy when fused under stellar conditions. The pressure falls, the core contracts. Electrons are driven into protons, neutrinos escape, and matter is compressed until almost no empty space remains between nuclei. What remains is not held up by burning fuel. A neutron star survives because matter behaves differently when particles are forced into the same small region. Quantum rules prevent identical particles from occupying the same state, creating degeneracy pressure. The strong nuclear force also contributes at very short distances. Together, these effects can oppose gravity after the thermal engine has failed. That support has a limit. Adding mass to an ordinary object often makes it larger. Adding mass to a neutron star can make it smaller. The extra weight increases the pressure in the interior, forcing the particles into a tighter arrangement. Gravity strengthens while the radius may shrink. The star becomes more compact, and the escape speed from its surface rises. A point is eventually reached where no stable arrangement of pressure can keep the surface outside the radius of a black hole. The limit is described through general relativity. In a neutron star, gravity is not simply a force pulling matter inward through an unchanged background. Mass and energy curve space-time, and pressure also contributes to that curvature. This creates an unusual difficulty. Pressure is needed to resist collapse, yet pressure itself adds to the gravitational source. The star fights gravity with something that makes gravity slightly stronger. A stable neutron star must satisfy a balance at every depth. Pressure is highest near the center and falls toward the surface. The pressure gradient must be steep enough to hold the material in place, but not so steep that the required pressure becomes impossible. The equations associated with Tolman, Oppenheimer, and Volkoff describe this balance. Their result is not one universal mass written independently of nature. It is a framework that takes the behavior of dense matter and asks which stars can remain stable. That behavior is summarized by the equation of state. It describes how pressure changes as density rises. A stiff equation of state produces pressure rapidly under compression and can support a heavier star. A soft one allows matter to compress more easily and leads to collapse at a lower mass. The exact form is uncertain because the central density of a neutron star exceeds what can be maintained in any laboratory. Nuclear experiments provide limits. Particle theory provides possible interactions. Observations decide which combinations survive. Every massive neutron star acts as a test. Pulsars above 2 solar masses show that dense matter cannot become too soft too early. Any model predicting collapse below those measured masses must be incomplete. GW190814 pushes the question farther. A companion near 2.6 solar masses would require support beyond the range, securely demonstrated by known neutron stars at the time of the event. It would not merely extend a record. It would remove entire families of interior models. The maximum mass usually discussed for a mature neutron star refers to a cold object rotating slowly enough that centrifugal support does not dominate its stability. This is sometimes called the non-rotating maximum, even though no real neutron star is perfectly still. It serves as a reference point because rotation can temporarily increase the amount of mass a star can support. A rapidly spinning star feels an outward effect strongest near its equator. The additional support can allow a neutron star to remain stable above the non-rotating limit. Such an object is often called supramassive. It is not free from collapse, as it loses rotational energy through magnetic radiation, particle winds, or gravitational waves. The extra support weakens. If its mass exceeds the non-rotating limit, the star may eventually collapse without gaining more material. Rotation cannot increase without end. A star spinning too quickly reaches a point where material at the equator would no longer remain bound. Instabilities can also carry angular momentum away. Uniform rotation may raise the supported mass by a moderate amount, but it does not make every equation of state compatible with a 2.6 solar mass neutron star. A different form of support appears immediately after two neutron stars merge. The remnant can be hot and rotating at different speeds in different layers. Differential rotation allows the inner and outer regions to share the burden in a way that a settled star cannot maintain. Such a hypermassive remnant may temporarily exceed both the non-rotating and uniformly rotating limits. Magnetic fields and internal friction gradually remove the differential motion. Collapse can follow within milliseconds, seconds, or longer. That temporary state does not easily explain the companion in GW190814. The smaller body existed in orbit before the final merger. It was not a fresh remnant supported by heat and turbulent motion for a few seconds. The binary had time to lose energy and spiral inward across a long gravitational wave history. If the companion was a neutron star, it had to remain stable as an old compact object. Its survival would speak to the lasting strength of dense matter. Temperature provides little rescue in a mature neutron star. Although the interior remains hot by terrestrial standards, it is cold compared with the energy scale set by particle degeneracy. Thermal pressure contributes far less than it does in an ordinary star. Cooling through neutrinos and surface radiation removes much of the original heat. The star remains because quantum and nuclear pressure continue after the heat has faded. Magnetic fields can shape the crust and channel surface emission, but they do not provide enough global support to carry a large amount of extra mass in ordinary neutron stars. Even magnetars remain governed mainly by gravity and the equation of state. The maximum mass is decided in the deep interior, where pressure and curvature meet. The idea of a surface becomes increasingly delicate near the limit. For any mass, general relativity defines a characteristic radius associated with a horizon. A neutron star remains a star only while its material surface lies outside that radius. As mass rises, the horizon scale grows. At the same time, stronger gravity compresses the star. The separation between the physical surface and the condition for a horizon becomes smaller. This does not mean the surface gradually turns into a horizon, while the star remains static. The two are different boundaries. A surface is made of matter. It can emit radiation, support a crust, and respond to tides. A horizon is causal. Once the star loses stability, collapse carries the material inward, and a horizon forms around the region from which no later signal can escape. The final stable configuration may exist close to the threshold, but no sequence of static stars continues smoothly beyond it. Near that threshold, small differences in the interior can decide the outcome. A slightly stiffer core may support another fraction of a solar mass. A phase transition that reduces pressure may trigger collapse earlier. Rotation may delay the moment. Accretion may bring it closer. The external mass can look almost identical, while the internal future changes completely. This is why GW190814 carries so much weight without revealing a surface. If the smaller companion was a neutron star, nature found a stable arrangement near 2.6 solar masses and preserved it long enough to enter a black hole binary. The pressure at the center would have been among the highest sustained inside any known star. The surface would have remained outside a possible horizon by only a narrow margin. If the companion was already a black hole, the same mass marks a different conclusion. Dense matter had reached its limit earlier, perhaps during stellar collapse, later accretion, or a previous merger. The object entered GW190814 with no material surface left to test. Its mass would sit just beyond the last stable star rather than just below it. The signal cannot place the companion on one side by weight alone, because the maximum mass is not known precisely enough. Theory permits a range. Observations narrow it. Each heavy pulsar raises the lower bound. Mergers, signals, and radius measurements restrict how stiff the equation of state can be. The allowed interval becomes smaller, but GW190814 remains inside the uncertain edge. Somewhere within that edge, pressure stops finding a stable answer to gravity. The change does not happen because matter runs out of particles or loses all pressure. It happens because no arrangement of pressure, density, and curvature can produce equilibrium. The last stable star is followed, not by a heavier version of the same object, but by collapse. The smaller companion approached the larger black hole, carrying either side of that transition. In one history, matter was still holding when the final orbit began. In the other, the limit had already been crossed. The waveform records the weight of the object with care, but the hidden balance inside it remains beyond the measurement. The surface of a neutron star is not where its strangeness begins. It is only the outermost boundary of a structure built under pressures that have no ordinary counterpart. A thin atmosphere may rest above the crust, containing ions and electrons pulled close to the surface by gravity. Beneath it, matter forms a solid layer. The word solid remains useful, though the conditions are far removed from rock, metal, or ice. Atomic nuclei arrange themselves in a lattice while electrons move between them. The pressure is already enormous, yet individual nuclei can still be recognized. Deeper down, they become increasingly rich in neutrons. Electrons are forced into protons, creating more neutrons and releasing neutrinos that escape during the star's formation. The nuclei grow heavier and more unstable as the density rises. At a certain depth, neutrons begin to leak out. This region is called the inner crust. Nuclei remain present, but they are surrounded by a sea of free neutrons. The separation between one nucleus and the next continues to shrink. Electric repulsion pushes positively charged protons apart, while the strong nuclear force draws nearby particles together. Neither interaction fully wins. Their competition produces shapes that do not resemble the nearly spherical nuclei found in ordinary matter. The nuclei may stretch into rods, flatten into sheets, or form connected structures containing tunnels and cavities. These arrangements are often called nuclear pasta because some resemble spaghetti, lasagna, and other familiar forms. The name is informal, but the physics is serious. The shapes may influence how heat moves through the crust, how magnetic fields evolve, and how the solid layer breaks under stress. The crust is thin compared with the whole star, yet it can support deformations larger than those possible in any material on Earth. A neutron star crust may be billions of times stronger than steel, under certain measures of breaking strain. That strength does not make it thick or gentle. Gravity presses every layer inward, and any fracture takes place under conditions where a small movement can release a large amount of stored energy. Farther down, the lattice disappears. Matter becomes a dense fluid dominated by neutrons, with a smaller population of protons, electrons, and perhaps muons. The density approaches that found inside atomic nuclei, and then passes beyond it. At this point, laboratory measurements become less direct. Nuclear experiments can study particles and collisions, but they cannot hold a star-sized quantity of matter at these pressures long enough to inspect it. The pressure inside the core depends on how particles interact when they are crowded together. At moderate nuclear densities, the behavior of neutrons and protons can be constrained by experiments and theory. At higher densities, the uncertainty grows. Small changes in the assumed interaction can produce different stellar radii and different maximum masses. One important quantity is the symmetry energy. It describes how the energy of nuclear matter changes as the balance between neutrons and protons becomes more uneven. Neutron stars contain far more neutrons than protons, so this term affects the pressure through much of the interior. A larger pressure at certain densities tends to produce a wider star. A smaller pressure allows greater compression. Radius measurements, therefore, reach inward indirectly. The outside size of the star carries information about forces operating in the core. The connection is not simple enough for one radius to reveal one composition, but a group of mass and radius measurements can remove many possibilities. The same is true of tidal deformation during mergers. A star that is easier to stretch usually has a larger radius or a softer outer core. A more compact star responds less. The deep core may contain only neutrons, protons, and leptons, but that is not guaranteed. Neutrons and protons are themselves made of quarks. Under sufficient pressure, their individual boundaries may no longer remain the most useful description. Quarks could move through a larger shared region, rather than staying confined inside separate particles. Such matter is often called deconfined quark matter. Its exact behavior remains uncertain. It may appear gradually as density increases, or through a sharper phase transition. The core might contain up and down quarks, with strange quarks appearing when the pressure becomes high enough. The word strange refers to the type of quark, not to the quality of the matter. Other particles may appear before quarks become deconfined. Hyperons are heavier relatives of protons and neutrons that contain strange quarks within them. In particle physics, their existence is established. Inside a neutron star, their presence is possible but not confirmed. The central pressure may make it energetically favorable for some neutrons to transform into these heavier particles. New particles create additional ways for the matter to arrange itself. That often lowers the pressure at a given density. The equation of state becomes softer, and the maximum supported mass falls. This leads to what is sometimes called the hyperon puzzle. Dense matter may naturally produce hyperons, yet neutron stars above 2 solar masses require enough pressure to avoid collapse. The puzzle does not mean hyperons are impossible. It means that models containing them need additional repulsive interactions or other forms of stiffening at higher density. Similar difficulties appear with some forms of quark matter. A phase transition may soften the core, making the star more compact and easier to collapse. If pressure rises strongly again after the transition, the star may recover enough support to remain stable. The result can be an equation of state that changes character with depth. Matter may be relatively soft at one range of density and stiffer at another. Two stars with similar masses could then have different internal structures. One might contain mainly hadronic matter, built from neutrons and protons. Another might contain a transformed core with quark matter, or another phase. Some models even allow a second branch of stable stars. A neutron star could increase in central density, pass through a strong phase transition, and settle into a more compact configuration without immediately becoming a black hole. Stars on the two branches might share nearly the same mass while having different radii. These hypothetical pairs are sometimes called twin stars. No clear observation has confirmed such a branch. Still, the idea shows why mass alone cannot describe the core. Two objects can weigh the same, while pressure and composition follow different paths inside them. Near the maximum mass, those differences become decisive. One interior may remain stable. Another may have no stable configuration at the same weight. A companion near 2.6 solar masses would push the central density into the region where these uncertainties matter most. If it were a neutron star, the core could not become too soft. Hyperons, quarks, or other phases might still exist, but their interactions would have to preserve enough pressure to hold the star outside a horizon. That requirement would reach through the entire equation of state. A model cannot be chosen only to support a large maximum mass. It must also agree with neutron star radii, tidal deformation, nuclear experiments, and the speed at which pressure disturbances travel. Causality places a hard condition. Information cannot move through the material faster than light. An equation of state made extremely stiff at high density may support a heavy star, but it can fail elsewhere. It may predict radii larger than observations allow. It may produce tidal effects inconsistent with merger signals. The interior, therefore, has to fit inside a narrow corridor. It must remain soft enough to match compact stars, and stiff enough to support the heaviest ones. GW190814 placed useful limits on this corridor. During that merger, two neutron stars distorted each other as they spiraled together. The measured tidal response suggested that neutron stars of ordinary mass are not excessively large. The electromagnetic aftermath also provided clues about the remnant and the amount of material ejected. Those observations do not give one exact maximum mass, but they restrict the range of equations of state. Heavy pulsars apply pressure from the other direction. A model that predicts collapse below their measured masses cannot be correct. Together, pulsars and mergers squeeze dense matter theory between survival and compactness. The equation of state must support more than two solar masses, while avoiding stars that are too wide or too easily deformed. The smaller companion in GW190814 stands near the far end of that squeeze. If it had a surface, its core would represent one of the strongest known cases of matter resisting collapse. The central pressure would be immense, yet pressure would still rise enough with density to maintain equilibrium. The star might contain exotic particles, but those particles could not weaken the structure beyond recovery. If it was a black hole, the same interior possibilities remain important because they help locate the boundary it had crossed. The object's identity would then say that no stable equation of state permitted matter to remain outside a horizon at that mass. The black hole interpretation still depends on understanding neutron star matter, even though no matter is visible in the final object. The hidden core therefore determines the meaning of the signal. It decides whether 2.6 solar masses can belong to a star, how small that star would be, and how strongly it would respond to the tide of a larger black hole. It also decides whether the absence of light is expected from a compact surface or from a horizon. Nothing from the core reaches a telescope directly. The crust covers it. Gravity bends the radiation, leaving the surface. The merger ends before the interior can be exposed. Knowledge arrives through secondary effects: mass, radius, cooling, spin, deformation, and the survival or collapse of the star. Each effect is incomplete. Together, they begin to describe matter that cannot be held in a laboratory. The path inward moves from a lattice of nuclei to free neutrons, from distorted nuclear shapes to a fluid core, and perhaps from particles into phases not yet identified with certainty. At the center, the old names may still apply, or they may have already given way to another form. That uncertainty is not separate from GW190814. It is the reason the companion remains difficult to classify. The object sits at a mass, where the deepest layers decide whether a surface can exist at all. Beneath the crust, matter either finds one final arrangement that holds, or the last stable structure disappears. The sky did not answer GW190814 with light. After the gravitational wave signal had been identified, observatories searched the probable region of the source across optical, infrared, X-ray, radio, and gamma-ray wavelengths. No transient could be connected to the merger with confidence. The result appears simple at first. Two black holes can merge in darkness, so a dark event may seem to favor a black hole companion. The difficulty is that a neutron star can also disappear without leaving enough matter outside the final horizon to shine. Light from a compact merger does not come from gravity alone. It requires material. In a neutron-star collision, some matter may be torn away, heated, decompressed, and thrown into space. Radioactive nuclei form inside the ejecta, and their decay powers a glow that changes color and fades over several days. This is called a kilonova. A surrounding disk may launch winds. Magnetic fields may help create a narrow relativistic jet. When that jet interacts with nearby gas, delayed radio and X-ray emission can follow. The binary neutron star event, GW190814, showed how much information light can add. Its gravitational waves revealed two compact masses in orbit. The electromagnetic emission traced matter outside the remnant. Telescopes watched a transient brighten and fade in a nearby galaxy. Spectra and color changes carried evidence of heavy element production. The event could be studied through geometry and matter at the same time. GW190814 did not provide that second view. The gravitational wave was clear, but no confirmed counterpart followed. The comparison with W10C081c is useful only if the physical differences remain visible. GW811 involved two neutron stars of broadly similar mass. Both carried surfaces. Both could deform. Their collision created several paths by which matter could escape. GW190814 contained a black hole above 20 solar masses and a much smaller companion. If the smaller body was a neutron star, it approached a large horizon alone. A black holoneutron star system produces light only under favorable conditions. The neutron star must be disrupted outside the horizon, and enough material must remain outside after the plunge. The disruption radius depends on the star's mass and radius. The capture region depends on the black hole's mass and spin. The orbit adds another condition. These factors decide whether the neutron star is opened to the outside universe or carried inward, almost whole. The larger black hole in W190814 makes a dark outcome easier. Its horizon is broad enough that a compact neutron star can cross before the tide removes much material. A lower-mass black hole would often create stronger disruptive effects outside its horizon. The heavier object shifts the meeting point inward. Matter may begin to stretch during the last orbit, but if the critical deformation happens too late, the released material cannot remain outside. Spin can change this balance. A rapidly rotating black hole, with spin aligned to the orbit, alters the location of the innermost stable paths. Under some conditions, This gives the neutron star more opportunity to be disrupted before capture. A slowly rotating black hole, or one with less favorable alignment, tends to swallow the star more cleanly. The spin measurements from GW190814 restrict some possibilities, but they do not define the final geometry well enough to turn darkness into a verdict. The neutron star itself may also hide the evidence. A massive neutron star is generally expected to be compact. The same pressure law that allows it to support unusual weight can place its surface close to the radius associated with collapse. Strong self-gravity binds the outer layers tightly. The tide has less time to expose the interior. A 2.6 solar mass neutron star, if stable, could therefore be harder to tear apart than a lighter and wider star. This reverses a familiar expectation. A more extreme neutron star might seem more likely to announce itself. In practice, its greater compactness can make it quieter. The object may contain a crust, fluid layers, and nuclear density matter until the final moment, yet leave a signal that resembles a black hole plunge. Matter can be present and still remain observationally silent. The absence of a kilonova therefore limits the amount of material that escaped, not the existence of a surface by itself. A bright optical or infrared transient would have favored a material companion. No transient means that any ejecta were either absent, faint, poorly placed, or missed. Several of those conditions can occur without requiring the companion to be a black hole. Distance matters. GW190814 occurred close enough for telescopes to follow a relatively faint source across many wavelengths. GW190814 was much farther away. Light spreads as it travels, and a transient that would be obvious nearby can fall below detection limits at greater distance. A merger producing only a small amount of ejecta could remain hidden even during an extensive search. Sky localization adds another difficulty. Gravitational-wave detectors identify a region of probability rather than a single point. Telescopes must search many fields, sometimes containing large numbers of galaxies and unrelated transients. A faint source can be overlooked, observed too late, or found without enough evidence to link it to the merger. The search may be thorough while still remaining incomplete. Viewing angle also shapes what reaches Earth. A narrow gamma-ray jet can miss the line of sight. Even when a jet is present, its prompt radiation may be weak or invisible from the side. Later emission from the jet's interaction with surrounding gas may brighten only after weeks or months, and its strength depends on the density of the environment. A dark result at one wavelength and one time does not guarantee silence everywhere. The host environment remains unknown as well. A merger in sparse interstellar space gives outflowing matter-little gas to strike. A similar event inside denser material can produce a stronger afterglow. Without a secure host galaxy, the age and composition of the surrounding stellar population remain uncertain. The same merger physics can therefore lead to different observed brightness. Non-detection is most powerful when theory predicts a signal that should have been visible. If a model requires a large amount of ejecta and a bright kilonova at the measured distance, the missing light weighs against it. Models in which the neutron star is swallowed promptly remain harder to test. They predict very little emission from the beginning. Darkness agrees with them, but agreement does not identify whether the infalling object had a surface before capture. A black hole companion offers the cleanest explanation for the silence. Two event horizons merge. No crust is torn open. Neutron-rich matter expands and cools. The final black hole releases energy, mainly through gravitational waves, while the surroundings remain dark unless unrelated gas is present. The electromagnetic result fits naturally. Its mass then becomes the difficulty. A black hole around 2.6 solar masses sits below the familiar population from older X-ray observations. The event is easy to understand at the moment of merger and harder to explain before it. Some process must create a low-mass horizon and place it beside a much heavier black hole. Darkness solves one part of the story while shifting the uncertainty into formation. The neutron-star interpretation has the opposite shape. Its formation and survival require very stiff, dense matter, or some additional rotational support. The high mass is difficult. Once such a compact star is allowed to exist, however, the darkness may follow from the encounter. The heavy black hole can erase the expected signature before enough material escapes. Neither interpretation is free of tension. This is why the missing light does not close the case. It changes the relative weight of possible histories, removes the brightest disruption scenarios, and leaves the darkest ones intact. The evidence is useful precisely because it is conditional. A surface is not directly observed by the light it would emit while intact. In a merger, the useful light comes from material that survives outside the horizon. A neutron star can possess a surface throughout the in-spiral and still fail that test. Once the surface crosses the horizon, its earlier existence becomes inaccessible. The final darkness cannot reconstruct what was hidden before the crossing. This creates a strange asymmetry between detection and absence. One confirmed kilonova from a boundary mass object would establish that matters existed outside a horizon, in at least one such system. Repeated non-detections would accumulate more slowly. They could indicate a population of low-mass black holes, or neutron stars so compact that heavy black holes usually swallow them cleanly. The pattern would need many events with known distances, spins, mass ratios, and search limits. But GW190814 remains the first kind of silence rather than the final kind. It is one event with favorable gravitational wave data and an unfavorable electromagnetic outcome. The sky did not reveal debris, but the geometry of the system already provided several reasons why debris might never have become visible. The absence of light, therefore, belongs inside the physical story, not outside it. It describes the final encounter between a small compact body and a much larger horizon. It limits what escaped. It says that the merger did not leave a bright, confirmed material aftermath. It does not say with certainty whether matter was absent before the plunge. The event speaks in one channel and remains quiet in another. Space-time carries the orbit across hundreds of millions of light-years. Photons provide no confirmed account of a surface, a disk, or expanding ejecta. Between those two outcomes lies the narrow possibility that a star existed, held together, and vanished before its material could announce itself. If the smaller companion in GW190814 was a neutron star, then matter survived at a mass where survival is no longer expected to be easy. The object carried between roughly 2.5 and 2 2/3 times the mass of the Sun. That weight had to remain outside a horizon before the merger began. No temporary heat from a fresh collision could support it. No short-lived differential rotation could hold one layer against another. It had to exist as an old compact body, settled enough to orbit a black hole, while gravitational radiation slowly removed energy from the system. The demand begins with the maximum non-rotating mass. For every equation of state, There is a heaviest cold neutron star that can remain in equilibrium without rapid spin. Below that limit, pressure can still oppose gravity. Above it, no stable solution remains. Collapse follows, and a horizon forms around the matter. A neutron star near 2.6 solar masses would push that limit upward. Models in which the core softens early would fail. Some equations of state allow new particles or phase transitions to appear at high density, but those changes often reduce the pressure available to support the star. If such a companion remained stable, any exotic phase inside it would need to behave differently. The core could change composition, yet the pressure would have to recover or remain strong enough to prevent collapse. That does not require an interior made only of ordinary neutrons and protons. Every new ingredient must fit the same balance. Hyperons could appear if their interactions provide enough repulsion. Quark matter could occupy the center if it does not remain too soft. A phase transition could occur without removing the star's ability to carry its own weight. The measured masses of heavy pulsars already press in this direction. PSR GW190814-0607 rotates more than 700 times each second and has a reported mass near 2.35 solar masses, with an uncertainty of about 1/10 of a solar mass in a recent analysis. It stands among the heaviest neutron stars measured so far. Its existence shows that dense matter can support well above 2 solar masses, though its rapid rotation contributes some additional support. Even that pulsar remains below the central value, inferred for the GW190814 companion. The difference is not enormous on a stellar scale, but near the maximum mass it is physically severe. The last few tenths of a solar mass can separate an object with a surface from one whose collapse is unavoidable. Pressure has less room to adjust. The center becomes denser, space-time curvature grows, and the radius may shrink rather than expand. Rapid rotation offers one possible margin. A uniformly spinning neutron star can support more mass than a non-rotating one, because centrifugal effects reduce part of the inward burden, especially near the equator. The gain depends on the equation of state and the spin rate for some stiff models. A star near the GW190814 mass could remain stable without rotating close to its breakup limit. For softer models, even the fastest uniform rotation would not be enough. Spin, therefore, cannot be used as a universal rescue. It changes the boundary, but the interior still decides how far the boundary can move. A star rotating near breakup would also become flattened, with a wider equator and a different response to tides. Its formation history would need to explain how that angular momentum was acquired and preserved until the final orbit. Accretion is one possible route. A neutron star in an earlier binary can pull matter from a companion over a long period. The incoming gas transfers both mass and angular momentum, gradually spinning the star faster. Many millisecond pulsars are understood as products of this recycling process. Their old magnetic fields weaken, their rotation accelerates, and their masses can increase. Reaching the GW190814 range would require an unusually long or efficient history of mass transfer. Each added layer would carry the star closer to instability. The donor would have to supply enough matter without causing collapse too early. Later, the neutron star would need to join a binary with a much heavier black hole. Dense stellar environments can exchange compact partners, but this is not an ordinary ending. The star might instead have been born unusually heavy. Core collapse does not produce one exact neutron star mass, and stripped stars in binaries can leave remnants different from those of isolated stars. Still, forming a stable neutron star near 2.6 solar masses at birth would place the newborn object immediately beside the collapse threshold. A small amount of fallback after the explosion could push it across. Survival would require the explosion to remove the surrounding layers with careful timing. The internal structure needed for such survival would also affect the star's radius. A common expectation is that an equation of state stiff enough to support a very heavy neutron star must make ordinary neutron stars too large. That connection is real, but not unavoidable in a simple form. Matter may be relatively compressible at lower densities and become stiffer deeper inside. Ordinary stars can then remain compact, while the most massive stars receive extra support from their inner cores. The mass-radius relation need not be one smooth, obvious curve. A transition may soften the core, followed by stronger repulsion at greater density. The resulting star can carry a large mass without making every lower mass neutron star wide. Observations from GW190814 mean and pulse profile measurements constrain this freedom. Neutron stars of ordinary mass cannot be made arbitrarily large without producing tidal deformation or surface geometry inconsistent with the data. Heavy pulsars prevent the opposite extreme. Dense matter must pass through a corridor between stars that are too wide and stars that collapse too soon. A 2.6 solar mass neutron star would narrow that corridor sharply. Some models could remain. Many would not. The surviving interiors would need enough pressure at the highest densities while preserving acceptable radii at lower masses. The result might favor a rapid stiffening deep inside the star, or strong repulsive interactions among particles that have not yet been tested directly. The same compactness that makes the object difficult to support could help explain why it remained hidden during merger. Heavy neutron stars are expected to have strong self-gravity and relatively small tidal deformability. The larger black hole would pull across the star, but the surface might resist visible disruption until very late. Little matter would remain outside the horizon. No bright kilonova would be required. This is the quiet reversal at the center of the neutron star interpretation. The more massive and compressed the star becomes, the less clearly it may behave like matter during the final observable orbit. A lighter neutron star could be opened by the tide, spilling material into a disk. A heavier one could carry a more severe internal state while leaving a cleaner, darker waveform. Its existence would also alter the interpretation of neutron star mergers elsewhere. The maximum non-rotating mass helps decide whether a newly merged remnant collapses immediately or survives for a time. A higher limit allows more remnants to remain outside a horizon, while heat and rotation support them. That extra survival time can change disk formation, mass ejection, neutrino emission, and the brightness of the resulting kilonova. A high maximum mass would not guarantee long-lived remnants. The total mass, angular momentum, thermal state, and equation of state still matter. It would shift the thresholds. Systems previously expected to collapse promptly might instead pass through a brief hypermassive or supermassive stage. The light seen from those mergers would need to be read under a different set of limits. The mass gap would change as well. A confirmed neutron star near 2.6 solar masses would move the upper edge of the neutron star population upward. The interval between known stars and known black holes would become narrower, and perhaps partly overlapping. Mass alone would lose even more of its power as a label. Objects in the same interval could then have different structures. One could be a star, supported by a stiff core and rapid rotation. Another, only slightly heavier or formed through a different history, could already be a black hole. The transition would remain physically sharp for each object, but the population would overlap when viewed only through mass. None of this establishes that the companion was a neutron star. No pulsations were observed. No surface emission identified it. No clear tidal phase shift or electromagnetic debris appeared. The interpretation remains conditional. It describes the state of dense matter that would be required if a surface existed before the plunge. That condition is already valuable. It turns the unknown companion into a test. Either the object was a low-mass black hole, or matter found a way to support more weight than securely identified neutron stars have yet shown. In the second history, the final orbit carried one of the last stable stars toward a larger horizon. For a few remaining cycles, pressure still answered gravity. The crust remained above the core. The surface remained outside the radius, from which light could not return. Then the orbit ended, and the distinction disappeared from view. The star, if it was a star, crossed the boundary only at the final moment. Until then, matter held. If the smaller companion in GW190814 was a black hole, then its final moments become easier to describe. Two horizons move through a tightening orbit. No crust bends under the tide. No nuclear matter is pulled into a stream. No surface reaches the edge of disruption. The smaller horizon enters the larger one, and the system settles through gravitational waves into a single black hole. The difficulty lies before that final orbit. A black hole with a mass near 2.6 times that of the Sun is allowed by general relativity. The theory does not require stellar black holes to begin above some fixed minimum mass. Any amount of matter, compressed inside the corresponding gravitational radius, can form a horizon. Nature, however, must provide a way to arrange that compression. Ordinary stellar collapse often produces remnants in two broad groups. Some collapsing cores halt as neutron stars. Others continue inward and form black holes that gain additional mass from the surrounding star. The transition between the two outcomes may not leave many objects just above the neutron star limit. Once a horizon forms, matter that might otherwise have been ejected can fall through it, increasing the final mass. This is one reason the older observations appeared to contain a gap. Neutron stars gathered below it, and black holes in X-ray binaries generally appeared above it. The pattern was never perfectly measured, but it suggested that stellar death moves through the boundary in a jump. A low-mass black hole would show that at least one path can stop soon after the horizon forms. Such a path requires the dying star to lose most of the material that could fall back. A close companion can help. During earlier stages of the binary, the star may expand until its outer layers flow toward the companion or escape from the system. Hydrogen and helium envelopes can be stripped away, leaving a compact core with much less material around it. When that core collapses, the explosion may remove part of what remains. If the central object crosses the neutron star limit, but receives little additional fallback, the resulting black hole can stay close to the boundary. The process must be balanced. Too little collapse leaves a neutron star. Too much fallback produces a more familiar black hole of several solar masses. Binary interaction makes that balance less unlikely than it would be for an isolated star. Mass transfer changes the size of the core, the composition of the outer layers, and the angular momentum available at death. The companion can remove fuel long before collapse and alter the supernova that follows. A low-mass black hole may therefore be the final result of two stellar history rather than one. The same binary must then survive. A supernova removes mass from the system and can push the newborn compact object with an asymmetric kick. A strong kick may break the pair apart. A weaker one can leave the objects bound but change the orbit to produce GW190814 through isolated binary evolution. The system must pass through the deaths of both stars, retain a black hole above 20 solar masses, create a much lighter compact companion, and finish with an orbit tight enough to merge within the age of the universe. That is possible in models. Though it is not a simple sequence, the large mass ratio carries a record of uneven stellar evolution. One star retained enough mass to leave a heavy black hole. The other lost enough mass, or collapsed in a different way, to leave a remnant close to the neutron-star boundary. Both outcomes had to occur without destroying the binary. A second route begins with a neutron star, rather than a black hole. The star may be born below its maximum mass, and remain stable for a long time later. Matter transferred from a companion increases its weight. Rotation can delay collapse, while the star spins rapidly. As angular momentum is lost, or as more material arrives, the equilibrium can fail. The collapse of a neutron star into a black hole can leave a horizon only slightly heavier than the star that preceded it. Most of the mass is already concentrated inside a region, only a few tens of kilometers wide. There is no large envelope that must fall inward afterward. The new black hole can therefore remain close to the maximum neutron star mass. In this history, the object crosses the boundary before GW190814, but not during the death of its original star. It spends part of its existence with a surface and part without one. The final black hole merger hides that transition. The measured mass records the result, but not the time at which the surface disappeared. The collapse may release energy through neutrinos, magnetic fields, or a brief rearrangement of surrounding material, but it need not create a long-lived bright source. If the event happened far earlier than the merger with the larger black hole, no associated light would remain. The object would enter the final binary as a quiet low-mass horizon. A more layered possibility contains an earlier compact merger. Two neutron stars can collide and form a black hole after losing some mass through gravitational waves, neutrinos, and ejected matter. The remnant can naturally fall into the lower mass black hole range. It is not the corpse of one star, it is the combined remnant of two. That remnant must then find the heavier black hole in an isolated binary. This would require a more complicated system, perhaps a hierarchical triple in which two inner objects merge, while a third compact body remains bound farther away. After the inner merger, the new black hole continues orbiting the outer companion. Gravitational radiation, or later dynamical changes, can eventually bring the second pair together. The final signal would contain no direct mark, saying that one component had already passed through an earlier merger. Mass and spin might offer clues, but neither provides a guaranteed history. A low-mass black hole made from two neutron stars could appear similar to one formed by delayed collapse or unusual stellar fallback. Dense stellar systems offer another way to join unrelated remnants in globular clusters and nuclear star clusters. Stars and black holes move through crowded gravitational environments. More massive objects tend to sink toward central regions through repeated interactions. Binaries form, encounter other bodies, exchange partners, and sometimes harden into tighter orbits. A low-mass black hole created by a neutron-star merger could later replace a lighter member of another binary. A heavier black hole is especially effective at acquiring companions during close encounters. Repeated interactions remove orbital energy and increase the chance that the final pair will merge through gravitational radiation. This route does not require the two components of GW190814 to share a common stellar childhood. They may have formed at different times from different progenitors. Their pairing can occur much later, after the cluster has rearranged its compact population. The unusual mass ratio then reflects the environment rather than a delicate sequence inside one original binary. Gas around an active galactic nucleus provides a related but different setting. Compact objects embedded in a dense disk can exchange energy and angular momentum with the gas. Their orbits may become more aligned with the disk, and migration can bring them into regions where encounters are common. Black holes can form binaries, merge, and remain inside the disk long enough to merge again. A small black hole inside such an environment might gain mass through accretion or through an earlier merger. It could later pair with a heavier object and create a system resembling GW190814. These scenarios remain uncertain because the structure and lifetime of such disks vary, and the rate at which they assemble compact binaries is not yet securely known. A primordial origin moves farther from established stellar pathways. Black holes formed from unusually dense regions in the early universe could in principle possess masses within the old gap. They would not need supernovae, neutron stars, or stellar companions to create them. Their later participation in a binary would be a separate problem. No feature of GW190814 requires that explanation. Primordial black holes remain hypothetical, and observations limit how many can exist across different mass ranges. A stellar or dynamical history uses populations already known to nature. The primordial possibility stays at the edge of the discussion, because mass alone cannot identify origin. The low-mass black hole interpretation therefore contains several paths, none established by the signal itself. A stripped star may collapse with little fallback. A neutron star may gain mass and fail later. Two neutron stars may merge into a small horizon. A dense cluster or gas disk may assemble the final pair. Each route places the same object on the black hole side of the boundary, while giving it a different past. Spin could help separate some histories. A black hole formed through a recent merger may retain substantial rotation. A black hole made by delayed neutron star collapse could inherit the angular momentum of the star. Stellar collapse can also produce spin, while repeated interactions may tilt it away from the orbital direction. The measurement from GW190814 does not resolve. The smaller companions spin well enough to choose among these options. A population will eventually be more useful than one event. If many low-mass black holes appear in isolated-looking binaries, stripped stellar collapse or delayed neutron star collapse may become more plausible. If they cluster in systems with misaligned spins and repeated merger signatures, dense environments may be favored. The distribution of masses, spins, eccentricities, and host locations can turn formation history into a statistical question. For GW190814 alone, the black hole possibility remains physically simple at the end, and complicated at the beginning. The object carries no surface into the final orbit. Its darkness is expected. Its tidal response leaves no material signature. The strange part is how a horizon came to exist at such a low mass, and how it found a companion almost 9 times heavier. In this history, gravity won before the recorded signal began. Matter may once have occupied the object as a star, a stellar core, or 2 neutron stars moving toward an earlier collision. By the time it entered the last in-spiral, those distinctions had been hidden behind a horizon. The waveform carried the mass forward. The origin stayed behind. GW190814 was once described as though it had placed a single stone inside an empty field. The companion, near 2.6 solar masses, appeared almost alone, surrounded on one side by measured neutron stars, and on the other by familiar stellar black holes. A single event could not show whether the field was truly empty. It could only prove that one compact body had crossed it. 3 years later, another signal arrived from the same uncertain range. GW230529 was detected on the 29th of May, 2023, during the opening part of the 4th observing run. Only the LIGO Livingston detector was taking useful data at the time. The signal was therefore heard through one instrument, rather than triangulated across a full network, leaving its position on the sky broad, and its weaker properties harder to separate. The inspiral itself was long enough to measure 2 compact masses. The heavier component fell between roughly 2.5 and 4.5 times the mass of the Sun. The lighter one lay between about 1.2 and 2 solar masses. Those intervals are statistical ranges rather than exact weights, and they overlap more than one possible classification. The smaller body fits naturally among neutron stars. The heavier body lies where the old lower mass gap was expected to begin. The event differed from GW190814. There, the ambiguous object was the lighter companion to a black hole above 20 solar masses. In GW23529, the boundary object was the heavier member of a much lighter pair. The 2 events entered the same region of the mass map from opposite directions. The heavier object in W230529 was most likely a black hole under many population assumptions, though the gravitational wave alone did not provide an absolute material verdict. Its mass remained below 5 solar masses with very high probability. That placed it clearly below the range, once treated as the ordinary lower edge of stellar black holes. A compact body was no longer touching the gap from one narrow point. Another event had reached farther into it. One detection can be dismissed as an unusual path. 2 do not define a population, but they begin to change the shape of the question. The issue moves away from whether any compact object can exist between the familiar groups. Such objects have now been measured through their gravitational influence. The question becomes how often they form. What fraction are neutron stars? What fraction are black holes? And whether the distribution between them is smooth or thin. The word gap can be misleading. It suggests a forbidden interval, a clean white band with no inhabitants. The original evidence never required such perfection. It came mainly from compact objects in the Milky Way found through radio pulsars and ray binaries. Those methods selected particular systems. Radio measurements favored neutron stars with beams that crossed Earth. Ray measurements favored black holes, drawing gas from visible companions. Dark objects without those arrangements could remain unseen. A shortage in a catalog can therefore come from nature, observation, or both. Stellar collapse may genuinely produce fewer remnants in some mass ranges. Detection methods can deepen the shortage by missing the ones that do form. The resulting picture can look like a wall even when the underlying distribution is only a valley. A valley contains fewer objects, not none. Gravitational wave catalogs are beginning to measure that landscape through mergers. They bring their own selection effects. A compact object must belong to a binary that survives, tightens, and reaches coalescence within cosmic time. Heavy binaries can often be detected across greater distances because they generate stronger signals, while lighter systems spend longer in the sensitive band, but may be visible through a smaller volume. The observed mergers are not a direct census of every neutron star and black hole in the universe. Even with those limitations, the cumulative population has become large enough to test whether a completely empty interval remains plausible. The fifth gravitational wave transient catalog contains hundreds of compact mergers. Its population models do not favor a perfectly vacant region between 3 and 5 solar masses. The density may fall there. It may form a trough between a neutron star concentration at lower mass and a black hole concentration farther up. The trough is no longer consistent with being entirely blank under the models used in the analysis. This does not mean the old gap has simply vanished. A populated valley can preserve the physics that first created the pattern. Most collapsing cores may still avoid leaving remnants in the middle. Only certain stripped stars, weak explosions, delayed collapses, or earlier mergers may enter it. If those paths are rare, the number of objects falls without reaching zero. A smooth bridge and a sparse valley tell different stories. A bridge would suggest many outcomes at intermediate masses. A deep valley would suggest that the transition is abrupt most of the time, while unusual channels place a few objects inside it. GW190814 and GW230529 do not occupy identical positions within that landscape. The first ambiguous companion lies close to 2.6 solar masses. The heavier component of the second event extends upward through a broad range reaching 4.5 solar masses. Together, they show that compact mergers sample more than one point near the transition. Their companion masses also matter. GW190814 paired the boundary object with a black hole almost 9 times heavier. GW230529 paired its heavier boundary object with something likely to be a neutron star. One system may have hidden matter by swallowing it inside a large horizon. The other placed a possible low-mass black hole beside a star compact enough to test disruption and tidal effects. Different pairings expose different parts of the same population. GW230529 was detected by a single observatory, and that limits what can be claimed. The sky position remained poorly constrained. No narrow localization allowed telescopes to search one small region, with the efficiency available for some network detections. The signal strength was sufficient for a confident gravitational wave observation, but not for a precise measurement of every spin or tidal parameter. The boundary object remained classified mainly through mass and population probability. That limitation is useful in its own way. It shows that the ambiguity is not unique to GW190814. A detector can measure a compact object inside the transition region and still fail to identify its surface. Better sensitivity narrows the mass range. A full network improves localization and orientation. Stronger tidal information may reveal matter. The catalog is filling faster than the identities are becoming certain. Population analysis can work even when individual labels remain incomplete. Each event contributes a probability distribution rather than a fixed dot. Combined across many detections, Those distributions reveal where compact objects gather and where they become scarce. Many blurred lights can trace a distant city without resolving each building. The emerging distribution may contain overlapping populations. The heaviest neutron stars could extend upward through rapid rotation or stiff internal matter. The lightest black holes could extend downward through stripped stellar collapse, delayed neutron star failure, or merger remnants. In mass alone, the two groups may meet. Their physical structures remain different, even while their measured weights overlap. A star in this region holds matter outside a surface. A black hole of the same mass hides the interior behind a horizon. Population curves cannot remove that distinction. They can show how frequently each formation channel must operate and where overlap is likely. To assign individual identities, mass must be joined by tides, spin, light, and environment. The valley may contain several histories. Some black holes could form from stripped cores, while others are remnants of neutron star mergers. Some neutron stars may be born heavy, while others reach the boundary after long accretion. The same final mass can hide very different pasts. Spin distributions may eventually separate part of this mixture. A black hole formed from a previous compact merger may rotate differently from one produced by a slowly spinning stripped core. A recycled neutron star may retain rapid spin. Orbital tilt and eccentricity can point toward crowded stellar environments, rather than isolated binary evolution. None of these clues is perfect alone. Their combinations can reveal structure that a mass histogram cannot. The transition from gap to valley also changes how future events are described. A newly detected object near 3 solar masses should not be treated automatically as an exception to a clean rule. It belongs to a region already known to contain compact bodies. The task is to determine which branch of stellar or dynamical history placed it there. This change is quiet but important. Earlier catalogs encouraged a question built around absence. Later catalogs support a question built around scarcity and mixture. The map becomes less like 2 islands divided by open water and more like 2 highlands, connected through a low, narrow pass. GW190814 remains unusual within that pass. Its mass ratio is severe. Its smaller companion lies near the lower edge, and the large black hole could hide a neutron star before disruption. GW230529 adds a second kind of crossing, with a lower total mass and a likely neutron star companion. Neither event names every object involved. Together they weaken the idea that the boundary can be represented by a blank band. The 5th catalog adds statistical weight behind them. It contains no new neutron star source beyond those already known from earlier releases. Yet, the expanded black hole population and the full cumulative sample allow stronger tests of the low mass distribution. Under the collaboration's population models, a completely empty gap between 3 and 5 solar masses is effectively ruled out. What remains is the depth and shape of the depression. That shape will continue to change as detector sensitivity improves and more of the 4th observing run is analyzed. Some new events will land comfortably among neutron stars or black holes. A smaller number will settle in the valley. Those are the signals most likely to test supernova engines, dense matter, and the histories of compact binaries at the same time. The old white region is beginning to acquire texture. One point carries the name GW190814. Another carries the name 230529. Around them lie broad probability curves, selection effects, and formation paths that overlap without becoming identical. The gap is not closing like a door. It is becoming measurable as terrain. Across that terrain, mass remains the first coordinate, but no longer the final answer. The next evidence must come from the way each object responds when gravity presses against it. A valley can show where the bodies are. Their deformation may reveal what they are. Mass places an object on the map, but mass alone cannot reveal whether the object has a surface. Two compact bodies can weigh the same and still respond differently when gravity presses against them. A neutron star can change shape. A black hole, under the standard description of general relativity, does not reveal a material deformation in the same way. The distinction is small in the signal, but it is physical. The useful clue is called tidal deformability. As one body moves through the gravitational field of another, the near side feels a stronger pull than the far side. A star responds by developing a slight bulge. Its mass distribution shifts, and that altered shape changes the orbit by a small amount. The effect accumulates over many cycles. It does not arrive as one dramatic feature. It appears as a gradual change in the phase of the gravitational wave. The ease with which an object deforms depends on its compactness and its internal structure. A wider neutron star responds more strongly. A smaller star with the same mass resists the tide more effectively. The relation between the applied tidal field and the resulting deformation is often described through quantities known as tidal love numbers. The name comes from the mathematician Augustus Love, not from any emotional meaning. These numbers act as a measure of how much the object yields. For a material star, the response depends on the equation of state. Pressure inside the core determines how the star redistributes its matter under an external pull. A stiff interior can produce a different radius and tidal response from a softer one. The waveform, therefore, carries information from layers that no telescope can see directly. A classical black hole in general relativity behaves differently. For an isolated, non-rotating black hole in four-dimensional space-time, the static tidal love numbers vanish. The surrounding field can distort the geometry near the horizon. But the black hole does not retain the same kind of induced material, multipole, that a star does. In that limited but useful sense, the horizon does not yield like matter. This provides a fingerprint beyond weight. A body with a measurable, non-zero tidal response cannot be an ordinary black hole under that description. A body with no detected response remains harder to classify, because the effect may simply be too small for the instruments to resolve. Silence in the tidal channel resembles silence in light. It removes some possibilities without naming the object by itself. GW190814 sits inside this difficulty. If the smaller companion was a neutron star near 2.6 solar masses, it was probably very compact. Its tidal deformability would have been lower than that of a lighter, wider star. The large mass ratio also limited the contribution of the smaller body to the total phase. The final cycles occurred in a regime where the larger black hole dominated the motion. The detectors measured no clear tidal imprint. That result is compatible with a black hole. It is also compatible with a neutron star, whose response fell below the sensitivity of the observation. The waveform was strong enough to weigh the companion, but not strong enough to press on its surface and record a definite answer. A stronger event could change that balance. If a similar system occurred closer to Earth, the signal would arrive with a larger amplitude. More cycles could be measured with lower relative noise. A neutron star might then leave a phase shift too large to hide. The absence of such a shift in a sufficiently precise observation, would place a much tighter limit on any material response. The last orbit may carry another clue. A neutron star can be torn apart before reaching the black hole. When disruption begins, the compact body no longer follows the simple motion of an intact point mass. The waveform can weaken or end at a characteristic frequency. The exact cutoff depends on the star's radius, the black hole mass and spin, and the orbital geometry. A black hole companion has no crust to remove. Its inspiral can continue into a merger shaped by two horizons. The transition still contains complex strong field physics, but it does not include the breakup of nuclear matter. A clean continuation toward merger would therefore favor a horizon, if the signal were detailed enough to rule out a hidden compact star. The distinction is not a single switch. A neutron star may begin to deform without being fully disrupted. It may lose almost no matter outside the horizon. The signal may contain a weak tidal phase shift, but no visible cutoff. Different pieces of evidence can therefore appear with different strengths. Light becomes useful when disruption succeeds. Matter left outside the black hole can form a disk, eject neutron-rich material, and produce a kilonova or other emission. In that case, gravitational waves reveal the deformation, while photons reveal the debris. The two channels describe the same surface from different sides. A future boundary event may provide only one of them. A tidal signature without light could indicate that a star deformed, but was swallowed before much material escaped. Light without a clearly measured tidal phase might occur if the gravitational wave signal were weak, while the ejecta happened to be visible. The strongest identification would come from both. The ringdown belongs to a different part of the story. After the merger, the final black hole vibrates through characteristic modes before settling. Those modes depend mainly on the mass and spin of the remnant. Measuring several ringdown frequencies can test whether the final object behaves like the black holes predicted by general relativity. Ringdown does not directly reveal whether the smaller companion had a surface before capture. By that stage, the earlier object has already crossed the horizon. Its matter, if matter was present, contributes to the final mass and spin, but no longer remains available as a separate structure. The inspiral and possible disruption carry the better fingerprints of the companion. The ringdown examines the remnant. This division matters when designing future observations. Better low-frequency sensitivity gives access to more inspiral cycles, where tiny tidal effects can accumulate. Better high-frequency sensitivity helps near the point of disruption and merger. A detector that improves only one range may strengthen one clue while leaving another faint. The current ground-based network is limited by several kinds of noise. Seismic motion dominates the lowest frequencies. Thermal motion in mirrors and suspensions affects the middle range. Quantum fluctuations of laser light become important at higher frequencies. Engineers reduce each source in different ways, but none can be removed completely. Future observatories are designed to extend the listening band and increase sensitivity. Longer arms allow a given distortion of space-time to produce a larger change in path length. Underground sites can reduce some seismic and environmental disturbances. Improved mirror coatings, stronger lasers, and new optical techniques can lower other noise sources. With greater sensitivity, the observable volume grows rapidly. More compact mergers become detectable, including rare systems in the boundary region. The most valuable improvement is not only a larger number of events. Some nearby signals will arrive, with enough detail to measure effects that are invisible in the present catalogs. A small number of very clear detections may carry much of the information about tidal structure. Most events will remain distant or poorly oriented. Their masses may be measured while their surfaces remain hidden. A nearby boundary system, heard across several detectors, could contribute more to the equation of state than dozens of weaker signals. The detector network matters as much as the sensitivity of one instrument. Multiple sites improve sky localization, polarization measurements, and confidence that a feature is astrophysical rather than local noise. A broad network also increases the chance that several instruments are observing when a rare event occurs. Better localization brings electromagnetic observatories into the same measurement. Telescopes can search a smaller patch of sky more deeply and more quickly. A faint kilonova that would be lost inside a large region may become identifiable when the probable host galaxies are limited to a short list. Host information adds formation context. A merger found in an old stellar population may favor different pathways from one found in a young star-forming region. A location near the center of a dense cluster could support dynamical assembly. A position in the disk of a galaxy might fit isolated binary evolution. The nature of the object and the history of the system are separate questions, but the same observation can begin to address both. Spin offers another fingerprint, though it is less direct. A rapidly rotating neutron star can support additional mass and may produce precession or deformation. A low-mass black hole, formed through an earlier merger, may also spin quickly. The orientation of that spin relative to the orbit can indicate whether the binary evolved together or was assembled later through encounters. Eccentricity can add another layer. Isolated binaries usually lose eccentricity as gravitational radiation shrinks the orbit, reaching the detector band in nearly circular motion. Systems assembled through close encounters can retain more eccentricity. A measurable non-circular orbit would not identify a surface, but it could narrow the formation history of a low-mass black hole. No single fingerprint is likely to solve every event. Tidal deformability, disruption frequency, light, spin, eccentricity, and environment, each answer a different part of the problem. The classification becomes strongest when several clues point in the same direction. A boundary object is therefore more than a mass inside an uncertain interval. It can be described through a collection of responses: the amount it deforms, the point where it breaks apart, the matter it releases, the orientation of its spin, and the environment in which its binary formed. The old division relied heavily on weight, because weight was the easiest quantity to obtain. Gravitational-wave astronomy has made mass measurements available for objects that never shine. The next stage is to measure how those objects behave under pressure from a companion. A scale can show that two sealed containers weigh the same. It cannot show whether one contains a rigid stone and the other a dense fluid. A gentle push against the walls begins to reveal the difference. Tidal gravity provides that push on a cosmic scale. For GW190814, the push was not recorded clearly enough. The object entered the larger horizon without leaving a measurable material signature. Future systems may not remain so quiet. A slightly lower black hole mass, a wider neutron star, a faster aligned spin, or a closer distance could move the disruption outside the horizon and into view. Then the boundary would no longer be inferred only from population curves. It would appear inside the waveform as matter yielding before gravity. The phase would drift, The signal might end early. Light could rise from the debris. A surface that had remained theoretical would leave a physical mark. Until such an event arrives, the fingerprint remains faint but defined. Mass says where the object sits. Tides say how it responds. Disruption says whether matter escapes. Ringdown says what remains. Together, those stages can separate a star from a horizon without ever producing an image of either one. The boundary between a neutron star and a black hole is not a line drawn somewhere in space. It is a condition. On one side, matter still finds a stable arrangement. Pressure rises inward, particles resist compression, and a surface remains outside the radius, from which light can no longer escape. On the other side, no static arrangement survives. Collapse continues, a horizon forms, and the interior is removed from every later observation. For an individual object, the difference is not vague. A neutron star has matter, structure, and a surface. A black hole has an event horizon. The ambiguity belongs to the observer. Instruments can measure mass, motion, and sometimes spin with great precision, yet fail to record the property that would settle the name. GW190814 makes that separation clear. The smaller companion was not physically undecided. It was one thing or the other before the final orbit began. Nature did not place it halfway between a star and a hole. The uncertainty appears because the signal carried some information strongly and other information only faintly. Mass survived the journey across space. A direct sign of a surface did not. This is an important correction to the way categories are often imagined. A category can fail observationally without failing physically. The object does not need to belong to a new intermediate species, simply because its mass lies between familiar populations. It may be an extreme member of one known class. The problem is deciding which class has reached farther than expected. The older mass gap encouraged a simple picture. Neutron stars occupied the lower range. Black holes began several solar masses above them. Between the two sat a quiet interval that seemed to separate the last stable matter from the first stellar horizons. GW190814 placed a measured companion inside that interval. Later events showed that the region was not empty. The clean division became a landscape of probabilities. Mass remains central because gravity responds to it directly. Yet the maximum neutron star mass depends on more than weight alone. Rotation can delay collapse. Temperature can matter for a newly formed remnant. The equation of state determines how pressure rises with density. Formation history decides whether an object is born close to the limit, grows toward it, or crosses it long before a later merger. The same measured mass can therefore carry different meanings. A rapidly rotating neutron star may survive where a slower one would fail. A low-mass black hole may have formed from delayed collapse after a long period as a star. Another may be the remnant of an earlier neutron star merger. Weight provides the final total, not the path taken to reach it. This makes the boundary less like a wall and more like a threshold crossed under different conditions. The threshold itself remains real. The route toward it varies. Inside a neutron star, the approach to that threshold is written through pressure. The outer crust, the fluid interior, and any deeper phase all contribute to the final balance. If matter contains hyperons, quarks, or another phase at high density, those components must still support the observed mass. If they soften the core too much, collapse occurs earlier. If repulsive interactions stiffen the interior again, the surface may remain. A black hole removes those details from direct view. Once the horizon forms, the earlier composition no longer appears in the exterior gravitational field, in a form that can be read easily. The final object is described mainly by mass, spin, and charge, with charge expected to be negligible in astrophysical systems. A complicated stellar history can end in a remarkably simple exterior. That contrast gives the boundary much of its meaning. A neutron star preserves information through structure. Its radius, crust, cooling, spin, magnetic field, and tidal response all carry traces of matter. A black hole preserves mass and angular momentum while hiding the arrangement that came before. One side remains a laboratory, the other becomes a limit on access. GW190814 brought those two forms of knowledge into the same signal. The smaller companion was weighed as part of an orbit. The larger black hole supplied a strong gravitational field. The merger completed the transition to one final horizon. What could not be recovered was whether the smaller body had already crossed its own threshold before the two objects met. The absence of light deepened the uncertainty without creating it. A bright kilonova would have shown that neutron-rich matter escaped. A clear tidal deformation would have revealed a body that yielded under the external field, neither appeared. With enough strength, the event remained almost entirely geometric. Geometry is not empty. It reveals the masses, the asymmetry, the distance, and the final motion. It also shows the limits of classification based on a single property. A scale can be exact, while the label attached to the measured weight remains uncertain. Future catalogs will change the balance between exactness and identity. More detections will describe the low-mass population. Nearby events will provide stronger tidal measurements. Better localization will allow deeper searches for faint light. Some systems will place a boundary object beside a lower-mass black hole, making disruption easier. Others will contain two low-mass compact bodies and remain in the detector band long enough for small material effects to accumulate. No one event needs to answer every question. A population can reveal where the mass distribution dips. A few clear tidal signals can identify material objects inside that region. Electromagnetic counterparts can show when disruption releases matter. Spin and eccentricity can point toward formation in isolated binaries, clusters, triples, or gas-rich environments. The result will probably not restore the old clean map. It may reveal overlap. The most massive neutron stars and the lightest black holes can occupy the same range of weight while remaining different in structure. Classification will then require more than placing a point on a horizontal axis. This is already common elsewhere in astronomy. Two stars can share the same mass and have different ages, radii, and internal histories. Two galaxies can shine with similar brightness while containing different populations. Measurement becomes richer when one coordinate is joined by others. Compact objects are entering the same stage. GW190814 is remembered because it forced that change early. It did not offer a final identification. It showed that gravitational-wave astronomy had become precise enough to find an object at the place where older categories were least secure. The uncertainty was not caused by poor observation. Alone, it was caused by a physically meaningful overlap between plausible outcomes. That overlap reaches beyond one companion. It connects nuclear physics to stellar evolution. The strength of matter inside a neutron star affects whether a surface can survive. Supernova dynamics affect whether a low-mass horizon can form. Binary interaction determines which remnants remain bound. Dense clusters and repeated mergers create combinations that isolated evolution may rarely produce. Detector sensitivity decides which histories become visible. A single mass near 2.6 solar masses, therefore, touches several scales at once. It reaches inward to quarks and nuclear forces. It reaches outward to the death of massive stars. It reaches across millions or billions of years of binary evolution. Then it arrives at Earth as a fractional change in the length of a laser arm. The chain is long, but the recorded event is brief. That brevity gives the signal a quiet form. The orbit accelerates, the frequency rises, and the two bodies disappear into one remnant. There is no image of the smaller companion before the crossing. No telescope sees a crust or a horizon. The evidence is reconstructed after the wave has passed, through models tested against the changing phase. Even so, the boundary has become observable. It is no longer only a number estimated from nuclear theory, or a gap inferred between radio pulsars and X-ray binaries. It is now a region visited by measured compact objects. Each event places another constraint on how matter survives and how black holes begin. The eventual answer for GW190814 may remain uncertain. Better population models can change the probability assigned to each interpretation. But the original waveform cannot gain information that it did not contain. Its smaller companion may continue to be described with two possible names. That does not reduce the event's value. A scientific measurement can be important because it defines what is not yet known with greater care. GW190814 narrowed the uncertainty to a specific mass, a specific system, and a specific missing property. It changed a broad theoretical question into an observational target. The next boundary object may deform more clearly. Another may release a faint red glow. A third may appear in a system whose formation history can be inferred from its host environment. Gradually, the same uncertain region will separate into different populations and different paths. For now, the smaller companion remains at the center of a measured silence. It carried enough mass to strain the category of neutron-star, and too little to fit comfortably among familiar black holes. It approached a larger horizon, crossed it, and left behind no direct confession of what had crossed. The deeper lesson is not that the categories have become useless. Their meanings are sharper than ever. A surface and a horizon remain fundamentally different. What has changed is the confidence with which mass can be used as a shortcut. Near the boundary, the shortcut ends. Observation must slow down and gather several kinds of evidence before a name becomes secure. That demand suits the object itself. Nothing about a compact remnant near collapse is simple. Its weight, spin, interior, companion, and histories all meet in the final classification. The uncertainty is not a weakness in the map. It is a sign that the map has reached a region where one dimension is no longer enough. The final remnant no longer preserves that distinction outside itself. The waveform does. Not as an answer, but as a boundary made real. A place where matter may have held until the last moment, or where a horizon may have arrived long before, and where the instruments on Earth were precise enough to find the difference, but not yet precise enough to name it. The signal has already passed, and the mirrors have returned to stillness. Far beyond the reach of any telescope, the final black hole continues through space, with no light around it, carrying within its horizon the last trace of two separate bodies that can no longer be recovered. The questions remain outside. A surface may have existed until the final plunge. A horizon may have been there long before. The waveform does not need to answer now. It can fade into the distance with the same quiet rhythm in which it first arrived. Across the dark between galaxies, other compact bodies continue their slow orbits. Some will hold together for millions of years. Some will move closer with every passing cycle. Their waves have not reached Earth yet. For now, they remain part of a future sky, still traveling through the cold and almost empty spaces between stars. The room can become smaller again. The detectors, the distant binary, and the narrow boundary between matter and gravity can drift farther away. Breathing can settle into its own unmeasured pattern. The weight of the body can rest where it is, without needing to follow the last orbit, or hold any of the numbers that pass through the night. There is only darkness now, not the darkness of danger, but the quiet darkness between points of light. The old signal moves on beyond Earth, growing weaker as it crosses more distance. Nothing needs to follow it. The horizon remains far away. The room remains still, and somewhere beyond all familiar names, the universe continues without hurry, carrying its hidden objects through long and silent paths.